Hello, everyone, and welcome from wherever in the world you're joining us from today. Today's iStructE webinar in collaboration with Idea StatiCa will be on fire design for steel and concrete members. You'll have a chance to ask the Idea StatiCa team. We have Kostas and Marios with us today. Questions at the end of the webinar as well. And then I shall be sending across your CPD certificates for the webinar at the end. And I'll pass it over to Idea StatiCa now.
Thank you, President.
Okay, thank you. I hope you can hear me. Hello and welcome, everyone. Thank you for joining us today for this webinar delivered by us at Idea StatiCa in cooperation with the iStructE. As with our other webinars, our goal is to examine topics from both a theoretical and a practical perspective and help deliver more efficient, safer designs. This is the same today. In today's webinar, we'll be looking at the use of CBFEM in the context of fire design, and this will be both for steel and concrete structures. This is often a critical topic, particularly when it comes to the safety of the building occupants, the efficiency of the structure itself as well, and other similar considerations. And the ultimate goal for us is to allow a more advanced fire design for connections, for members, to be performed more routinely. So during the next hour, we'll discuss how CBFEM can be used to assess structural performance alongside fire conditions. So as mentioned before, my name is Marios Theokoropoulos. I'll be moderating the webinar. Joining me today is Kostas Hatzopoulos, our technical manager at Idea StatiCa UK, who will present you with the topic later on. So some basic information for those of you who might be new to GoToWebinar, who haven't used it in the past. On the right, you're going to see, hopefully now, the Grab tab. You can modify some settings there. I think you're all muted by default, but you should be able to ask any questions you may have at the bottom there, and then we'll review them during the session and at the end of the Q&A mostly. And so right, before we start and I pass over the presentation to my colleague, I'd like to start with a quick poll covering how you currently perform fire design checks. So I'm going to start that now. You should be able to see it. So I'm going to wait for a few seconds until everyone has a chance to vote, and then we can move on. A few more seconds. Okay. Right, so let's close that. Thank you. Now, let's take a look at the results. So these are the results. I can't see them very well because my screen's not participating with me, but if I recall correctly, most of you aren't very familiar with fire design, which is okay because we're going to be looking at this. Hopefully it'll give you a basis for your design, so you can use that. And some of you use the simpler, I think, calculations, so that's fine as well. Hopefully the more advanced analysis will be helpful for you as well. So for now. Okay, so I think we can proceed. Shall I pass over to you, Kostas?
Well, yes, pass over the presenter to me, Marios, and I propose to switch off our cameras to save some bandwidth and move on with the rest of the webinar.
Yep.
So So just could you please verify that you can see my screen and that everything is okay?
Yep, yeah, I can see the presentation.
Yes,
Okay, good, thank you. To be honest, I was surprised by the results of the poll because I was expecting that more people would be familiar with fire design. It appears that this is, although this is a hot topic, say, it appears that most people are not familiar with it. I was expecting that most of the people designing structure would be using simplified methods, also the so-called tabulating methods. However, the use of these simplified methods lead to the use of fire protection, and what we do as Idea Statica, which is called performance-based fire design, can save a lot of resources in this respect because it can save fire protection material, time, and it can also protect the environment, as fire protection materials are quite demanding from this perspective. So in this webinar, I will demonstrate the tools Idea Statica has developed to help engineers deal with the situation of fire design. So before moving to the actual presentation, it makes sense to make a short introduction into the principles of fire design. However, I will not go into great depth because this is a very big topic. So basically, for fire design, the generic procedures are described in detail in the context of Eurocodes in a specific part. This is EN 1991-12, which basically defines actions on structures exposed to fire. So in this part of the code, two design approaches are mainly identified, and the whole procedure is described in this diagram here. So the first approach is the one called prescriptive approach. In this approach, the code defines the so-called nominal fires to generate thermal actions. However, there is an alternative path, which is the performance-based approach. This approach is using fire safety engineering that refers thermal actions based on the actual physical and chemical parameters of the materials. In Idea Statica, we follow this second approach, and basically we're analyzing parts of the structure. To perform this kind of analysis and to follow the code provisions, we have developed tools that accurately determine mechanical actions. And to perform an accurate analysis, we have developed tools that can recreate the boundary conditions of the substructures and then analyze them using advanced calculation models. In this part of the code, it is also defined the load-bearing requirement of the structure during fire exposure. This is defined as an accidental design situation. And in this situation, the representative action of the variable load is defined as either a quasi-permanent value or a frequent one, depending on the national aims. Then the structure should be able to resist the loads calculated under this accidental situation, for what we call a fire resistance time, denoted with the letter R. And after this letter, the required time is defined in minutes. I will show you this later during the example. Another important aspect of this calculation is the selection of what we call the temperature time curves, which are basically the value of the gas temperature of member surfaces as a function of time. In idea statica, we have implemented the conventional curves that are defined in the code. Since this is a generic part that outlines the design procedure, following what we know in the Eurocodes, the Eurocodes are defining separate parts for each kind of material. Since in the context of idea statica, we develop solutions for steel and concrete, the relevant parts that are 1992-12 and 1993-12 also apply to our solution. I will start this webinar with an example for the design of a steel connection. To perform this design, we need to apply some additional rules from Eurocode 1993-12. Since in idea statica, we can roughly say that we always perform a materially nonlinear analysis that employs a stress-strain curve. Following the rules of this part of the Eurocode, we need to modify this curve for elevated temperatures. In general, this relationship is displayed in this graph. Basically, there are many graphs for many aspects of the calculation, many such graphs contained in the code. I will show you some of them in the upcoming slides. And in idea statica, we call this degradation curves to show that as the temperature rises, some of the resistance values drop. To say it simply, there are reduction factors for properties of the materials, either the steel or the concrete. In this case, we display this for the steel. And as the temperature increases, all of these reduction factors introduce a significant drop to the corresponding property. So let's move to our worked examples where we will use a simple fictional structure I have created in our global analysis software. So basically, this is a steel platform that is supported on two concrete frames. And from this structure, I will start by designing connection. And then in the second part of this webinar, I will also design a concrete frame using an advanced thermal analysis. So let's move into my global analysis software, where I have already calculated the structure. Let me activate the realistic view to see, to understand what is going on. This is, some loads are applied. This is the variable load. There are some cover loads, of course, self weights. Let's also move combinations, where I have defined several ultimate limit state combinations. obviously starting with the ULS prefix. There are also two serviceability combinations with the SLS prefix. And lastly, I have the fire design combination, which is obviously starting with fire. I have applied the Eurocode provision, and this combination is an accidental one, as you can see from the factor on the variable. So let me close this dialogue and move on. And let's move to the still design module of my global analysis software, where I have to open the still design settings because this matter. And here, first, we define what I was telling you, one of the most important properties of the design, which is the required fire resistance in minutes. So we're defining 30 minutes for this structure, which means that the load-bearing action of this platform will maintain its capacity for at least 30 minutes. Then what is important is the definition of the temperature time curve. In this case, we're using the default Eurocode curve, which is also known as ISO 834. This is the value we have picked. And then I'm asking my global analysis software to perform this fire design in the resistance domain. So let's close this dialog. I just wanted to show this value and perform the fire design check at the member level. I'm looking at green diagrams, meaning that all members are passing the fire design check. This means that we're ready to proceed with the fire design at the connection level, since everything is fine in my global analysis software. However, to perform this check, I need to export the structure to IDEA StatiCa checkboot, and I need to press this yellow icon here and wait for IDEA StatiCa checkboot to open. Basically, for this presentation, I have already exported the whole structure to save some time. So let's wait for checkboot to pop up. So there it is. Obviously, the whole structure is there, and we can see the steel members in blue and the concrete frames in gray. So I have also switched on the transparent view, which displays some cubes that denote the location of potential connections. I have also exported the members of the concrete frame that I will design in the second part of this webinar. And at this point, you may be wondering, why do I need to have an intermediate representation of the structure? The answer is that for both the connection check and the concrete frame check, we need to export substructures and create sophisticated sub-models that describe the behavior under the fire situation, and of course, under the ultimate limit state conditions, and to make sure that these sub-models can replicate the calculated behaviors that reflect the limit states, we must recreate their boundary conditions to match the ones of the global analysis model. This application, besides the geometry, we also import the loads and guarantee an accurate representation of all the boundary conditions. So, for example, I can display the moment or the shear force diagram. And also, if I open the loads dialog, I can see that I have imported all combinations, including the one for fire design and the serviceability. So enough with this introduction, and let's move. Let's pick the corner node and press the open button to design this into idea StatiCa connection. So let's wait a little bit for idea StatiCa connection to open. So there it is. And here we can see that the geometry of the node and the incoming members were imported. We also have imported combinations. And please note that all combinations ensure that no unbalanced forces exist. This means that this sub-model, this substructure, is under total equilibrium. So having selected the fire one combination, one can see that the unbalanced forces at the table below are all 0. Before we proceed with the actual fire design, I must connect these members and make sure that the node works under the ultimate limit state load. So for this check, I will deactivate the fire combination, and then I will move to our templating system called the connection browser, where I will open it and apply this template I have created. And here I will pick an 8.8 M30 bolt, apply it. The software guides me with some warnings graphically, so I need to make some corrections until all of these warnings disappear from the screen. So starting from operation cut 2, let me select corresponding stub. This is fixed. Let's move to cut 3 again. Select the corresponding stub. This is fixed. Warnings disappear. So we're ready to perform the ultimate limit state check, which is a precondition for fire design. If the connection does not pass the ultimate limit state checks by a big margin, it will also not be able to pass fire design check. So let's calculate the connection and check the results. And to do so, I need to press the calculate button. So at this point, a CBFEM sub-model is created. The load cases we have defined are applied in steps using a materially nonlinear analysis. So let's wait a little bit for the solution to complete. Okay, it will not take long. We're almost there. So after solution, a short summary comes up where we look at very low utilizations of bolts, welds, and plates. And to visualize this, we can activate what we call the overall check, which provides a colored view of the connection. Here we see that everything is gray, which denotes that everything remains in the elastic region. Now it's time to perform the fire resistance analysis. And to do so, I will make an identical copy of the connection and proceed with this type analysis. So here I have to switch the analysis type to fire design by clicking on the FIR button. So let's move back, and now that we will do the fire design analysis, I will deactivate all ULS combinations and activate the fire one, which again displays 0 unbalanced forces. It's under equilibrium. Now at this point, we need to define the material temperatures for the fire design condition. However, these are calculated in our global analysis software. So we need to move back there, identify the corresponding members, and check the calculated material temperatures in the report. So let me isolate the corner members. Okay, and then let's open the report to see what was calculated there. Let's wait a little bit for this regeneration. So we need to scroll down to the fire resistance table and seek for the value next to material temperature. So let's scroll there, and for this member, we have a value of 719.32 Celsius degrees. I have noted now the values for the rest of the members. So basically, we need to move back to idea StatiCa connection and set these values under the temperature category. I will start by setting the temperature for the column. So let me first select it, accept the selection, and set 719 degrees. Then create a new temperature which is 732 degrees, and then I will select the members, connection, right, accept selection. Here I have a short list of the selected members. So everything is okay, and this is it. Basically, I just need to perform calculation. So I will go straight and press the calculate button, and basically that was it. We just need to wait a little bit. Again, a materially nonlinear analysis is performed. However, this time we also take into account the material degradation curves as the fire temperature rises. This means that the yield stresses and strains are modified accordingly at every solution step. So let's wait a little bit for this one to complete. Okay, the calculation is over, and we can see basically that the checks were passed, except for these two bolts here. Now, this is very important because changing two bolts is a very cheap intervention. So we can just change two bolts and leave it as is, fulfilling the fire design requirements. The other option we have is to apply fire protection, which is a costly solution, and of course has high environmental demands. So let's move to the check and have a look at the rest of the results in more depth, where in the plates we can see, for example, summary of the results. And we can see that the magnitude of the yield stress is very low due to the high temperature. So we have a 50.8 megapascal yield stress in this case. Let's also move to the welds to see the same effect, where we can see for this temperature a very low stress resistance, which is reduced. I can also expand this row and see the calculation in code formulas, where we can see the reduction factors applied in these calculations. And we also have the same for bolts. So moving to the bolts tab, again, I can see that I have reduced resistances for the 732 degrees temperatures. And again, I can also expand this table and have a look at, okay, let me go back, checkpoint then to conclude this one. And yeah, let me save this connection, and I need to move back to my slides and move to concrete fire design slides. So moving to the introduction for my next example, which is fire design for the concrete frames, we have also defined in this structure. And in line with what was applicable for steel, before moving to the concrete, we also need to discuss a little bit about another part of the code for fire design. So once again, we define the drop of material strength following the rise of temperature using some diagrams. In this case, we're displaying two curves depending on the type of aggregate used for your concrete grade. Again, it is evident that as the temperature increases, the factors, the value of the factor is dropped significantly. We have similar curves also for the reinforcements. Here, again, depending on the type of reinforcement, we have many different curves. I will not go through every one of them. For concrete, we have another important factor in our calculation, and this is the moisture content of the member. This influences the specific heat factor here. And as we can see, it influences the calculation for temperatures less than 200 degrees. However, according to the code, for this specific parameter, we can conservatively neglect it from the calculation, basically by setting its value to 0%, which corresponds to dry concrete. So again, I will move to my global analysis software, where we will perform an advanced thermal analysis for the concrete frame displayed in yellow. And again, we will start from checkbot. So again, let's move into the checkbot, and basically I need to take the connections out of the way, and then select my concrete frame, which is now highlighted. Now to to perform a thermal analysis for this frame, I will need to open ID StatiCa member. So let's wait a little bit as this goes through the PIM link. And now the concrete frame came through into ID StatiCa member, maintaining the original geometry, but also it contains the lateral supporting members called related members in ID StatiCa terminology. At this point, some may consider this as unimportant. However, they are part of the substructure, transferring loads and providing lateral support. And since we're interested for an advanced analysis, it is important to account for their influence without providing results, of course, or checking them. So let me go to the project and activate the fire design to let the software know what we're going to do. I can see the fire exposure category, which means that the activation was okay. So as a first step for my thermal analysis, I need to define which of the imported combinations is the one meant for fire design. So I will go and select combination fire 1 and wait a little bit for its properties to come up. And as we wait, let's note that all loads from the analysis are displayed. You can see the load concentrations, the location of the middle steel beam, or at the location of the reactions, which is similar to what we had in the connection sub model. Basically, this is a substructure under equilibrium. So let's wait a little bit for the properties to come up. Having selected fire 1, I will set its check type to fire resistance. Now, ID StatiCa member identified that this is the combination meant for the fire resistance. And this is the reason that this group of connections contains only fire 1. So let's move to the settings, where we will set fire design settings. Click on this label. And as a first step, I will set the fire resistance class to R30 to match what I had on my global analysis model. Then I need to set my fire curve type, standard fire curve, again, the ISO 834, which is the one we also had in the global analysis software. We have some other options, of course. And another important aspect of the calculation is the material degradation, basically the curves I demonstrated during my slide. So here, starting with concrete, I can press these 3 dots here and bring up table in the form of table the drop of resistances as the temperature rises. We have the same for the reinforcement, similar table where the yield stresses drop as the temperature rises. So let's keep the settings by pressing the save button and move to the calculation. After saving this data, I need to define the fire exposure for my members. This means that I need to, for my columns, to create a fire exposure data group. Let me select columns. I'm looking at the preview below, so I will leave everything as is. This means that my column will be exposed to fire for every side. There is also an option to set the initial material temperature, which is set to 20 degrees. This is the code. This is the code default, and we will see later how is this used. We also have the concrete moisture. We will leave again a value of 1.5%. For dry concrete, this can be set to 0 or conservatively be neglected. So let's add another fire exposure category. This time I will select the beam. In this case, I will assume that there is a top slab, so its top edge will not be exposed to fire, and this will have an impact on the heat transfer analysis, as we will see later. Now, before performing the thermal analysis, we must also define reinforcements. So let's start inputting those. I will start from column P1. So let's select it. And I will use the provided wizards here to define the layout of the reinforcement. So basically we can define every aspect of the layout, the reinforcement layout. I will accept what is there. So basically this is it. This is a preview of the reinforcement for this column. I will press OK and then move other column as well to apply similar layout. Let's give these settings. Finally, I will also apply similar beam reinforcement for my column. Again, we have a wizard. So let's apply some values here. I will also add some sidebars. So let's press OK. I can see that reinforcement was applied, so I just need to press the calculate button to perform an initial linear calculation, basically to check if the applied reinforcement fulfill the basic code checks. So everything is green here. The applied reinforcement passes all checks. We have some question marks because I didn't import the SLS combination to check stress limitation and crack width to save some time. However, all other checks were performed. So for example, if I move to check tab, top, there it is. I can request display on the selected member the capacity diagram. So the checks are there, but we don't want to go through this. So again, let's move to the advanced thermal analysis. So I'm pressing the GMNA button to start a materially nonlinear analysis. Pressing calculate. So at this stage, the frame is split into multiple sections where initially a thermal analysis is performed using the heat transfer equations. Each of these sections is meshed using finite elements, and the heat transfer is calculated for the time indicated by the fire resistance class, which in this case is 30 minutes. And then the results of this thermal analysis are used as an initial state for the subsequent materially nonlinear analysis. Okay, this started. We need to wait a little bit. Won't take too long. Okay, so steps are performed for each of the calculation. Now, after the end of the analysis, the results for both the ULS and fire resistance are displayed. And before looking into the detailed results, it makes sense to make sure that these results are valid, because basically this is it. The unprotected frame passes all checks, but we need to ensure by performing a buckling nonlinear analysis that this materially nonlinear analysis is valid. And if this buckling analysis performed by pressing the LBA button, I will start it immediately. Basically, we will check if the critical factors calculated are over 15. Then we can safely assume that the results are valid. Otherwise, we need to carefully select and amplify appropriate buckling shapes that will serve as imperfections for the GMNA IA analysis, which is another advanced topic on its own. So let's wait for the completion of the linear buckling analysis. Again, it will not take long, and this is performed for every combination that is used for the thermal and the UL for every combination imported from checkpoint. Okay, so the linear buckling analysis is over. The software displays the buckling shape, and it also displays the minimum amplification factor, or alpha critical. Obviously higher than 15, this is 324. Which means that basically that the M&A results are perfectly valid, and our unprotected concrete frame can maintain its load-bearing capacity after 30 minutes in the fire situation. Since this is the case, we can move on and see the calculation results in more detail. So first, let's have a look at an overview of the calculation results, where we can see the critical utilization and its position, and the position of the corresponding critical section at the critical member displayed in this table. For every member, the table can be expanded to display other positions that you might need to interrogate. And now let's have a look at the results of the thermal analysis. So let me click on the temperature button. Again, the short table comes up, displaying the locations of maximum temperatures, concrete. We also can see the reinforcement, the temperature of the reinforcement. And clicking on the detailed button, the sections I was talking about are displayed on the frame. So let's select member B2 in the table, expand the positions and find the 0.06 position, click on the corresponding row. This will display the cross section highlighted in the graphical window. And below the table, we can see the calculated temperature gradients. Obviously, as the temperature increases as we move to the outer side of the column, while the inner temperature remains at 20 Celsius degrees, which was defined in the code and was inputted in the related settings. I could also work the other way around, so I could look for a section in the graphical window and click on it to display what is going on. So let me move to the beam and click section. Again, the window below the table is adapted. I can see the beam, and I can see that the top side, which was not exposed to fire, is a little bit different. It does not develop temperature. We have similar results available for stresses and strains that are the ultimate checks for this kind of the calculation. So pressing the stress button and keeping the code check to detailed, I can see the stress results for both concrete and reinforcement. Again, at the specific section defined by its position on member. So for concrete, the compressive stresses and compressive strains are calculated on based on the material degradation curve, and of course the heat transfer results for the corresponding cross sections. At the bottom, we're looking at a graphical stress distribution. Maybe if I click on reinforcement, I need to select the position, critical position, yeah, and switch back to concrete. And now there it is. I can see the distribution of the graphical distribution of stresses. We have similar results available for strain, but I will not go through them because time flies. And basically what matters for the calculation is the stress and strain utilization displayed in the table above. We could also have a look at the stress results for the reinforcement. So I need to move to the reinforcement tab again. So let's have a look at the critical position of member B5. So again, let's expand this. This is at the location 0.06 meters. I'm selecting this, and at the bottom I can see the reinforcement bars colored depending on the stress level. I can also touch them with my mouse, and I can have a look at the exact calculated stress value for each one of them. And in the table above, besides stresses and strains, utilizations are also displayed. So I can conclude this example. I can also close this example because we're running out of time. So I just need to save this back to checkbot. The results of the calculations, of both calculations, are saved here. And then I can return back to my PowerPoint for my closing slide, where the key takeaways for idea StatiCa is that we have created a way that as we have demonstrated, we have created a workflow that offers you the option to perform an advanced analysis in a very easy way. You can perform an easy transfer of an accurate sub-model of the structure under equilibrium checkboot. The whole file design workflow is streamlined. So even for structures that are very demanding in terms of analysis, like for example, structures that require GMNIA analysis, everything is very easy. And of course, the results are intuitive and interpretable for every step of the calculation. So I think we have a little bit of time to move to our Q&A session. So Marius, if there are questions that we could answer quickly.
We have a couple. Can you hear me?
Yeah, basically, we do not have too much time, so
Yes.
maybe you can pick a couple of them and we could, for example, answer the rest through email or something.
Yeah, so an initial one just for housekeeping. We had a question that was asking whether the slides to the webinar can be shared by email.
Yes, we have to discuss this and maybe we could share. Yeah, why not?
Okay. And
basically, the recording of the webinar will be available in YouTube, so you can have the whole webinar available.
There are a few more. I think we might need to grab them from support. There were some that one I've noted. Can this method be applied to both painted and galvanized steel?
Painted and galvanized steel. Well, I'm not sure. I have to discuss this with the development, and maybe I'm not sure. Okay. Because we need, I think we need to have different curves, and I'm not sure if we can have user-defined curves at this point.
I think, yeah, for galvanized steel that might be tricky, and for painters, I'm not sure either. We could probably revisit this. Yeah. And is it possible to analyze a concrete encased steel column, or indeed masonry encased, I suppose, as well?
Well, for the moment, no, because there is no way to define it in idea StatiCa in idea StatiCa checkboot.
Yep, that's correct. Do we have time for another one, or there's
maybe another one if it's pick something simple and then.
There are a couple that they're more theoretical. One is asking if the frame was temporary and supporting a fire-rated self-contained generator in a shipping container, what would be the fire rating? I think that might be more of a code-based question in this case. So I'm not sure if we can answer that. And final one. So checking my understanding of the steel design feature, it seems the tool can be used to check the design of fire-rated and unprotected steel connections, where other software has already been used to validate the design of the fire-rated plus unprotected members. Let's see here. So I think this is basically asking if there's been a validation, understood correctly.
To be honest, I do not.
I'm not too sure. I think it's basically asking if the connections are checked, the file design for the idea connection side of the design, and the members are checked separately. But I suppose you can check both through member.
Yeah. And I think that I'm not sure if I don't think that members support the checking of still members yet. We need to, this is a topic for further development. This is something that we will support in the future. So yeah.
Yeah, so connection specifically members.
And concrete
separately.
Members for
and
now.
Concrete members, yeah. Okay.
So I think we can close this here.
Yes, yeah.
We're out of time. So basically, thanks. I would like to thank everyone for attending. And we will come back to you through email for the rest of the questions we have asked into the chat.
Yes, thank you for attending, everyone.
Yeah, bye.